Bismillahirrahmanirrahim. Okay, we will discuss Bellman Ford algorithm again, and this is a recap of the previous lecture. If you remember that we talked about the number of iterations Bellman Ford will do, which is in this case v minus 1 is the number of maximum edges that are required to connect two nodes of a graph. So in this case, this is the maximum number. Remember that this, or you can say this is a worst case scenario, and I have discussed that in the last lecture. Just I am going to write few important points, and then we will move on towards the topic of linear programming. So in this case, why there are v minus 1 iterations? Because as I mentioned that if I want to connect S to some other arbitrary node, let's call it Vn, then in this case at most there will be 1, 2, 3, so on up till n minus 1 number of edges. So which means this means that all the vertices of the graph are traversed before reaching to the destination node. Okay, remember that this is the worst case. That means there will be many cases in which we do not have to traverse all the nodes. Rather, by traversing a significantly less number of nodes, we can move from S to that particular node. But this is not the worst case scenario. In the worst case scenario, we will traverse all the possible. Okay, remember that we cannot have a situation in which we have more than n minus 1 edges in a path, not in a simple path. Remember that we are talking about a simple path. It is impossible to find greater than n minus 1 edges in a simple path. Remember that a simple path is the one in which we do not have any loop, and we can transform any non-simple path into simple path by removing the repeating edges without adversely affecting the shortest path. Why is that? Remember that once we remove a repeating edge from the path, that will not have any negative impact on the path, because we are reducing the number of edges. And if that edge has a positive impact on the overall path, that means we are still reducing it. So that means we are not making it worse. So that is why it will always improve upon the previous case. That is the justification behind v minus 1 iterations. So hopefully this is clear now, that why we have v minus 1 iterations. Next, remember that why this algorithm will work fine. What is the correctness proof? That is, during each iteration, let me write it, in the worst case scenario, one edge is allowed to be added to the shortest path. So let me show you a very simple example. These are this set of iterations. Let's say we start from the start node, and once we start, we do not have any path which is taking us from S to V, right? So that means the cost is infinity. This is our first iteration. In the second iteration, we will allow at least, this is again the worst case scenario, at least one edge to be relaxed, So let's say this is connected with some node, and after that again we do not have any path from, and this is now third. Again we will add a new node, and after that there is a no path, and so on and so forth. So you can see that after n minus 1 iterations, we will be absolutely sure that if there is a path between S to V, we have found it by using n minus 1 iterations, by adding n minus 1 in edges in the worst case scenario, and all these edges are relaxed after adding, right? For this reason, Bellman Ford algorithm will exit with all the paths relaxed. So this is an example of one of the possible paths. Example of one of the possible paths. So you can see that very same argument can be applied to any other path which we have in the graph. So that means it will be applicable to all the paths in the graph. So very same logic will apply over there. Now let's talk about the negative weight cycle. Technically, after n minus 1 iterations, all the paths must be relaxed due to this upper argument. If we perform one more relaxation relaxation iteration, it should have no impact on the shortest paths. Why is that? Because they are already in the most relaxed form, and it is impossible to relax it any further. But in case some paths are further relaxed, that is only possible if we have a negative weight cycle in the path. Why is that? What is the justification of that? So justification is, if we have a path, in this case let's say this is your S, you're going towards V, and after that there is a cycle. So if we add new nodes in the path, and if it is a negative weight cycle, then only then it will improve the shortest path. Because as we have already discussed, by using n minus 1 edges, you have found a path which is simple. All the other cases in which you are using more than n minus 1 edges after that, so that means it is only possible if you have a negative weight cycle. So I hope that now this is clear that how it actually works and what is the logic behind it. Okay, that was the brief introduction of our previous lecture. Let's move on towards the lecture which we have to discuss today, and that is discussion on linear programming. I have given a brief intro of the linear programming last week, and I will discuss it further in today's lecture. So whenever we are talking about linear programming is a paradigm in which we try to solve a problem in which we have different constraints, and constraints needs to be satisfied while optimizing certain objective function. This is linear programming. Uh, for example, if we have let's say 5 different variables x1, x2, x3, x4, x5, then they can be different. For example, 5x1 plus 2x2 plus 3x5 should be greater than is equals to 5. Now this is a constraint, right? Similarly, we can say that 2x2 plus 3x1 plus I don't know, x5 is greater than is equals to 2, and so on and so forth. So we can have many different constraints. So these are the constraints. And at the same time, let's say our objective function is that x1 plus x2 plus x3 plus x4 plus x5 should be maximum, right? So in this case, there is no optimal value. Rather, we are trying to maximize it as much as it is possible by satisfying all these constraints which are mentioned. So this is linear programming. Now there is a simpler version of this linear programming which is called system of system of difference constraints. Let's say if we add a restriction that each constraint should have one should have only one coefficient value 1 and other -1, rest all should be 0. That means what? That we cannot have more than two values, two variables in a constraint. For example, I can write x1, that means it is multiplied by 1, minus x1 minus 1 x3 should be less than is equals to 20. Now this is a constraint which is in the form of system of difference constraint, right? So difference constraint because we are talking about a difference of two values. Similarly, I can write something 1 multiplied by x2 minus x5 less than is equals to 10. Now this is also an instance of system of difference constraint. In this case, you can also think of it like this, that let me rewrite it. It is same as saying that 1 multiplied by x sorry, not 1, it is 0 multiplied by x1 plus 1 multiplied by x2 minus 1 multiplied by x3 plus 0 multiplied by x4 plus 0 multiplied by x5 should be less than is equals to 10. So in this case, we have only these two values, one is 1 and other one is -1, rest all are 0. So this is an example of a system of difference constraint. So in this case, we are talking about linear programming, and in linear programming we are talking about a special case in which we have to solve system of difference constraints. So in case of system of difference constraint linear programming, where each row of A contains exactly 1 1 and 1 -1 and rest all are zeros. So this is what I have written over here. So let's say if we have a constraints written in this form, that means x1 minus x2 is less than or equals to 3, and all these are example of system of difference constraints. So if I write in a generic way, so that means we are always talking about some variable xj minus xi should be less than is equals to wij. So for the time being we are talking about less than is equals to, but this can be even greater than or greater than is equals to, but for the time being let's keep it simple and think of it as these are the simple constraints, system of difference constraints in which we have less than is equals to sign. So all these constraints should be written in this generic form, so keep that in mind. Xj minus xi should be less than is equals to wij. Okay, so now I think these constraints are quite easy, and you can solve it by just looking at them, that what are the possible values which satisfy these constraints. So in this case, if you look at x1, x2, and x3, is x1 is equals to 3, x2 is equals to 0, and x3 is equals to, this is a possible solution to this problem, right? So you can find it because it is a relatively easier problem. Now why we are discussing this problem in shortest path? That means there has to be some kind of a link between system of difference constraints and the shortest path which we are discussing right now. So let's say if I transform my system of difference constraints into a constraint graph in which all these constraints which are in this form xj minus xi less than is equal to wij can be transformed into this form, in which what we have xj is corresponding to this wj, this xi is corresponding to this vi, and this wij is the edge weight between these two nodes, right? So the value on vj will be xj, and the value on vi will be xi, and keep that in mind that the direction, this is a directional thing, right? So keep that in mind, this is directional, in which we are going from vi to vj. So that means that the minus sign, the one with the minus sign is the source one, and where we end up is the one which has the positive coefficient. So keep that in mind. It is important that you exactly know that how we can convert a system of difference constraints into a constraint graph. So rest all are zero, so we don't have to worry about that. So in this case you can say that we are transforming our difference constraint into a constraint graph. Now the thing is, there are certain theorems which are helpful in this particular scenario. For example, the first theorem says that if the constraint graph contains a negative weight cycle, then the system of difference is unsatisfiable. So that means what? That if we can, after transformation of system of difference constraints into constraint graph, if I find a negative weight cycle, then we can say that there is no solution of system of difference constraint, right? So this is the theorem. Now that means what? That let's say, okay, if I want to transform this system of linear system of difference constraints into a constraint graph, what will be the final graph? Let's say in this case, using this representation, we will have a one v2, which is the originating one. From I'm talking about this one, right? 1. So this should terminate on v1, and the path, sorry, edge weight should be 3 in this case. And there is another one, V3 with V2. So that means there is a V3 which is connected with V2, and in this case the edge path is, sorry, edge weight is -2. Then there is another one which is starting from V3 and going towards V1, and its edge weight is 2. So that means if I transform it into this, so in this case I have this constraint graph. So you can see that there is no negative weight cycle, no negative weight cycle. Therefore there should be a solution to this problem, and this is one of the solution which I have already mentioned. So keep that in mind. So this is how you will convert a system of difference constraint into a constraint graph. So let's talk about this theorem now. So proof is, let's say, suppose that a negative weight cycle, there is a negative weight cycle. So that means what? We have a V1, V1 goes to V2, V2 go to V3, and this goes up till to some edge, some vertex V4, VK, and this comes back to the starting node, because we are talking about a negative weight cycle, and this whole thing is less than 0. So that means it is a negative weight cycle. So we are starting from V1 and we are ending at the same V1. That is why it is a cycle. So this is the definition of a cycle. So if we have a cycle, so that means V1 to V2 and so on, and terminating on V1, then that means what? If I look at this only one, so in this case V1 to V2, so V1 to V2 means what? That means we, as you remember that the starting node is the negative one. So if I write it in the form of a constraint, that means we are talking about x2 minus x1 less than is equals to the edge weight between these two, and we are calling it the edge weight between 1 and 2 as w12. Similarly, if I write it for this second constraint, it will be what? X3 minus x2 should be less than is equals to w23, and so on and so forth, right? So if I write the last one, the vk21, so that means what? That means we have x1 minus xk should be less than is equals to the edge weight between wk1. So that will be the last value in the whole thing. So if I look at this one, so you can see that there are many values which are cancelling out. For example, this one is cancelled with this one is cancelled with this one, and if I keep on writing these one, these will also be cancelled out, as you can see over here, right? So we'll get a 0 over here, and 0, that means we have all these values on the left hand side is less than on the right hand side. True? So in this case, that means 0 should be less than is equals to what? Should be on the right hand side. On the right hand side, as you know that we are talking about the edge weight of this one plus this one plus this one, and this whole thing is less than 0. Because of negative weight cycle we have less than 0. So that means what? That 0 is either less than 0. So it means what? That is less than some negative value, right? So that is what we have over here. So this means what? Okay, 0 is either less than some negative value and 0 is equals to some negative value. Both are not possible. So both possibilities are not there. So because of this we have a contradiction, and it is impossible to find the solution for a constraint graph with negative weight cycle. So this is proven. The second thing is that now if we do not have any negative weight cycle in a constraint graph, then what will happen? Suppose we have no negative weight cycle in the constraint graph, then constraint graphs, constraints are, number one, are satisfiable. That is important. Number one, that means we have a solution to the constraint graph. The thing is, now question is how we can solve it. Number one, what we are doing is that this is a constraint graph. This is a simple constraint graph, and you can draw or you can write a system of uh, difference constraints from here. For example, if I write them, so there will be what? So first one is we have from v1 to v9, so that means x9 minus x1 should be less than is equals to w91, right? No, so not 91, w19. Okay, the second one is maybe this is first one. Then let's talk about this one. We have x1 minus x4 should be less than is equals to w41. And then let's talk about this one. So in this case we have uh, x4 minus x7 should be less than is equals to w71. Let's talk about this one. Then in this case x3 minus x7 should be less than is equals to w73, and so on and so forth. You can see that I can transform this constraint graph into system of difference constraints by looking at them. Okay, let's say we add a new vertex s to v with a 0. For example, if I add a source over here s and I connect all these nodes, well, let me draw it with different colors so that we let's say I use this. So these are the edges which we have added. That means I have connected all the vertices with S using edge weight of 0. So this is what we have done over here. So what is the benefit of that? As you can see, once I have done that, so this resembles with the problem which we have seen before, that this is your source and all these are the vertices which are connected with that, and we want to find shortest path between S to V1 VIs. We have done that before. Now question is why we want to do that while solving system of difference constraints. Remember that before going into that, let me answer one question, that whether adding this S or connecting this S with all the vertices with edge weight 0 will introduce a negative weight cycle in this whole graph, which was this initial graph rather. Yes or no? Answer is no, because these are unidirectional. It is starting from S and going to V1. There is no edge. There is no edge which is taking you back to S. So that means once you cannot go back to S, that means you cannot have a cycle. Let it be any cycle, positive cycle or negative cycle. So once you cannot go back to S, that means you cannot have a cycle. So that means what? That by adding a S to the graph and connecting it with 0 edge weight, it will not have any impact on the uh, overall graph, that it will not add any negative weight cycle in the graph. So keep that in mind. Number one. So if there is already no negative weight cycle previously, so that means I can satisfy it, or I can find the solution. Okay, the thing is, it is quite easy. As we have discussed before, the shortest path between S to any Vi is the solution to this particular variable. So for example, if I can find the shortest path between S to Vi, whatever is the value of the shortest path, that is the solution for this particular variable Xi. So this is our claim. It is of course not proven yet. So now we have to see that whether our claim is correct or is it logical or not? So for this, let's discuss this constraint graph in bit detail. Consider we have any constraint xj minus xi is less than or equals to wij, which is shown. This constraint graph is shown over here. So that means what? Your starting node is -1, that is vi. The ending node is positive, which is vj, and the edge weight between these two is wij. So that means it is a constraint graph which is developed over here. Now we are saying that the shortest path which is connecting your some arbitrary s to this vi, and there is a shortest path which is connecting your s to vj. So we have a shortest path between s to vi and s to vj. So this is what we have shown over here. If you remember that, this is what? This is triangle inequality. If you remember, we have discussed it before. So that means the shortest path between s to vj, which is this one, right? This is the shortest path. If we take a detour from s to vi first and then back to vj, then in this case the addition of these two will be either less than, no, not less than, sorry, is either greater than or is equals to this shortest path. Because if it is not this, if it is not, then in this case I cannot call this shortest path, rather this will become your shortest path. That's what we have discussed, and this is what is triangle inequality. So triangle inequality, using triangle inequality, we can rewrite this whole thing that is like this, that delta s vi, the shortest path between s to vi, is, sorry, uh, plus this path, that is shortest path between vi to vj, right, should be either, this should be either greater than or is equals to the shortest path between s to vj, right? So this is what is triangle inequality. So we have read that and we know that this is how you will write the triangle inequality. So okay, in this case, as you see that this wij is same as the is the edge weight between vi to vj, which is also the same thing as what? As vi on this one. This one is wij, and the shortest path between s to vi is what? That means this is your starting node, this is your ending, this is your ending node. So whatever is the value over here, that is the shortest path between s to vi, right? So this is how we solve it. And if you remember, while defining our constraint graph, the value which is stored on the vith node is xi, and similarly the shortest path between s to vj, that means the value on vj will be xj. So you can, by just plugging in the values, you can see that this is xi, this is your xj. So if I rewrite it, so that means what? That means if I take this as xj, this thing will come over here minus xi, and this is less than is equals to the wij, which is the same thing which we are talking about, the constraint which we want to solve. So that means what? By finding the shortest path between s to vi, the shortest path between s to vj, we can solve the constraints by transforming our system of difference constraint problem into a shortest path problem. Shortest path you already know how to calculate, so that means all you have to do is you have to pick the system of difference constraint, then you have to transform them into constraint graphs, constraint graph, and after that you have to then add a source s and connect it with all the vertices with zero edge weight, and then you have to find the shortest path between s to all the vertices. So that will give you SVI's for all the I vertices. And once we have done that, so in this case all you have to do is rewrite them in this form, and the values stored on the vertices will represent the solution of the problem. So in this case, for example, at the end of a day, whatever the value which will get xi over here, so that will be the solution of the problem. Simple as that. So this is how you will transform a system of difference constraint into the shortest path problem. So I think, so now it is very clear that what we have to do. Let me write it for you. Given system of difference constraints, for the given system of difference constraints, transform them into constraint graph using the same way, right? These are all in xj minus xi less than is equals to wij form. You have to transform into what? Vi to vj with wij on it. The value which is stored on is xi, and the value stored on is xj, right? So keep that in mind. And after the transformation, add a source node s and connect it with all the vertices with 0 edge weight. This will not, important thing is, will not introduce negative weight cycle unless there is already an active weight cycle. If there is already an active weight cycle, it will remain there. It will not have any positive or negative impact because of addition of this s. But important thing is, by just adding this s, we will not be introducing a negative weight cycle in our graph. So that means if the negative weight cycle is already there, it will remain there. And if it is not there, there will be no new negative weight cycle that will be introduced by adding this s. Once we have that, now solve this graph for single source shortest path problem, and finally the values on each node is the solution of the system of difference constraints. So this is how you can solve the system of difference constraints by transforming it into a single source shortest path. How you can do it? By using Bellman Ford over here. Bellman Ford is an algorithm. Okay, what will be the outcome of Bellman Ford? It will either give you the shortest paths, or second possibility is it will report a negative weight cycle. So in this case, you just have to write there is no solution of this system of difference constraints, right? So So Bellman Ford algorithm can solve a system of, why is that? I think you already know that we have a VE somewhere, right? So we have used VE. So this is the time complexity of the problem. So in this case, you can see that, okay, we have V number of vertices, or you can say V number of V number of variables and E number of constraints between them. So altogether it will take VE time. So M into N time will be used for that. Okay, so there are two more things which should be noted over here. Whenever you are using Bellman Ford to solve this problem, there are two, you can say, the side products or side effects of these of this problem solving mechanism. Number one is Bellman Ford maximizes all the variables, this x1, x2, x3, the sum of all these variables. It will try to maximize this because objective function. Do you remember that objective function in the linear programming? So think of it as an objective function which it is maximizing all the time, and by satisfying all the constraints which are there. So in this case, what you can say that linear programming, if you think from the linear programming point of view, you will say that I will try to maximize the sum of all the variables. This is your objective function, provided I will satisfy all the constraints. So that means by using Bellman Ford, both these things are satisfied, which is important. And the second, okay, one more thing is x size or always less than is equals to 0. Can you answer this? Why this is always less than is equals to 0? Pause this video for a moment and try to answer it yourself. Okay, if you remember that I have connected my S with Vi, Vj and so on. Let's say let's talk about only these two vertices. This is a 0, this is a 0, and there is, let's say there is a path between Vi and Vj. So in this case, as you can see that the shortest path between S to Vi is 0. Similarly, the shortest path between S to Vj is 0, and this will be kind of a, you can say that this is the initialized value because all the vertices are connected with the 0 edge weight, right? So this is whenever we add a source over here, it will be connected with 0 edge weight. So that means the shortest or the minimum distance which is known up till now from S to any vertex is 0. So down the line, if we try to improve upon it, so that means it has to be less than 0. It can, sorry, not like, it has to be less than 0. Otherwise, that means it will remain 0. You cannot go anything higher than 0. So because of this very reason, the shortest path values will be either 0 or it will be a negative number because of this very reason. So keep that in mind. And the last thing is, it will try to maximize the difference between the minimum and the minimum and the maximum value of the variable. So in that case, that means if you have x1, x2 and so on up till xn, so in this case the variable which has the highest value, which is h over here, and the variable with the lowest value over here, it will try to minimize the distance between these two values of these two variables. So this is also this is also a side effect of using this algorithm. So there is a very good application of this second point. If you look at a if you look at a VLSI layout, that means what? Just let me give you a very what do you call, layman terms explanation of this. Think of it that there are two components. These are electrical components 1 and 2. So in this case, what we want to do is, normally whenever we are designing a circuit, we will ensure that there is a minimum separation between these two components because they may interfere, because these are electronic circuit. So at least there should be some kind of a minimum separation between these two, right? And at the same time, what we want, that we want to keep them very compact. That means what, we are trying to make them very compact, very close to each other, but at the same time by maintaining the minimum separation between the two components. Do you understand what I'm saying? So that means overall our circuit design, your PCB or the layout will be really compact. At the same time it will ensure that there is no two components are closer than the minimum separation point. So think of it as a constraint, right? So if I call it component 1 as let's say x1, and this component 2 is x2, then in this case the difference between these two can be called as w12, which is the minimum separation between these two components. So you can think of it as a constraint. So in this case, if I write this constraint, it will be something like this: x2 minus x1. So this actually represents the distance between the two components should always be greater than is equals to some w, I don't know, w12, right? So this is different from the our original constraint, which has to be in this form: xj minus xi should be less than is equals to some wij. We can always transform this into this form by just multiplying the left and right hand side by -1. So minus, by doing this we will get x1 minus x2 should be less than is equals to minus w12, and now this whole thing is in this form and rest everything remains the same. So if I see that, so what we are trying to do is we are trying to ensure that the constraint, the minimum separation constraint, is not violated, number one, and number two, because of this second property that it tries to maximize this. So what it will do is it will try to it will try to ensure that maximum number of components are added in one direction. What does that mean? We have a component. Minimum separation is maintained. So that means in this particular direction, we want to maximize the number of components without violating any of the distance constraint. So this is the byproduct. So we can use Bellman Ford in this particular case. So that means what, we have to mention all our constraints in the form of system of difference constraints like this, and by applying the Bellman Ford it will automatically ensure that in one direction it will maximize the number of components and it will not violate the system violate the distance constraint. So in this case we will get a really compact design of layout. So that's all regarding the Bellman Ford algorithm. So in the next lecture, I will discuss about a more generic problem solving technique in which we will, instead of just talking about single source shortest path, we will talk about all pairs shortest path.